This is assignment 2.2, steady state exercise. This assignment was based off of research that was carried out by our class to investigate the impact of steady state exercise on blood pressure, heart rate, stroke volume, breathing rate, lactate levels, and O2 saturation. The test was a simple exercise bike test where we had the test subject work aerobically for 20 minutes. I also had to provide evidence and explanations for the results, as well as investigation into anomalies and what they meant. The hypothesis provided a prediction for what the results would be, and the method was used to describe the test and how it was carried out. According to thefreedictionary.com, steady state exercise is an activity that achieves a balance between the energy required by working muscles and the rate of oxygen and delivery for aerobic ATP production. Steady state exercise is where the level of exercise remains the same, and so does the heart rate. An example of this would be a long distance cycle where you are constantly working at the same intensity. There are several different types of hypothesis. A null hypothesis is a hypothesis that agrees with an average. A two-tailed hypothesis is when the prediction is higher or lower than the average, and a single-tailed hypothesis is if you predict one value will be specifically higher. For example, in a coin toss, I predict there will be more heads than tails in 10 tosses. In steady state exercise, we predict there will be a gradual increase in heart rate and it will then plateau. There will then be a rapid decrease. For the respiratory system, during steady state exercise, we predict there will be a rapid increase in breathing rate and it will then plateau. O2 saturation during steady state exercise will increase and then it will plateau. For blood pressure, we predict that in steady state exercise there will be an increase in systolic pressure and it will then plateau, and the diastolic pressure will either slightly decrease or remain the same. For lactate levels in the blood, we predict that there will be a decrease. For energy systems, we predict that the subject will use the aerobic energy system. Energy systems during steady state exercise. There are 3 stages to the aerobic energy system, which are aerobic glycolysis, the Krebs cycle, and the electron transport chain. Stage 1. Aerobic glycolysis. When PC is not available, there is a build-up in adenosine diphosphate. This creates phosphofructokinase, and this initiates a breakdown of glucose, and the enzyme that does this is called glycogen phosphorylase. However, this time oxygen is available, and it reacts with the enzyme coenzyme A, which will stimulate acetyl-CoA. The yield of phosphate of this process is 2 phosphate molecules. Because of the presence of oxygen, pyruvic acid does not form lactic acid buildup. Stage 2. The Krebs cycle. This uses acetyl-CoA formed in aerobic glycolysis, and it is formed into oxaloacetic acid. This is then made into citric acid. The citric acid then goes into the Krebs cycle, where 4 byproducts are formed, which are CO2, hydrogen, a yield of 2 phosphates, and oxaloacetic acid. The oxaloacetic acid goes back to form citric acid and the process reoccurs. The 3rd stage is the electron transport chain. Hydrogen formed from the Krebs cycle is used and combines with NAD and FAD. This combination forms NADH and FADH, which forms the electron transport chain. NADH forms H+ hydrogen ions and binds with oxygen to form H2O. FADH forms H- electrons. This stimulates the creation of 34 phosphate molecules. The aerobic energy system is used for events such as marathons as long as there is a constant supply of oxygen. The method. Start by measuring the weight of the test subject and find 2% of this weight. To add to the exercise bike, find the height of the test subject and adjust the seat so it is comfortable. Also measure the breathing rate, blood pressure, heart rate, lactate levels and O2 saturation before exercise begins. Then start the exercise with a 3-minute warm-up with no weight. This warm-up simulates the actual exercise and warm-up of the muscles that will be used. Next, measure the heart rate every minute so there is a large quantity of data and we can see the change in heart rate over the 20-minute period. Also, measure the O2 saturation every minute using the pulse oximeter. Measure the blood pressure and the breathing rate every 2 minutes. This will allow us to see the change in oxygen. This will allow us to see the change in blood pressure and breathing rate over the time of the exercise. The RPE or Borg scale, which is the rate of perceived exertion, is to be given every 5 minutes to make sure the test subject is working aerobically and not working too hard. Measure the lactate level at the start, middle and end of the exercise using a finger prick which will be administered by the teacher. This will take a small amount of blood and analyze the lactate levels. One job is also to make sure one person is keeping track of time and they will ask for readings from everyone. This cannot be done all at once, so one person is measuring heart rate and Borg scale, one person is measuring breathing rate and oxygen saturation, and one person is measuring blood pressure. Each person will have a table and will make a note of the reading, and then give it to the timekeeper so that this person does not have too much information to hear and write down all at once. The timekeeper will have their own piece of paper with the data for every reading. Also take all readings post 1 minute and also take all readings post 3 minutes. Heart rate. Heart rate will increase because an increase in movement is detected by proprioceptors. As well as this, there will be a lack of oxygen in the blood and an increase in CO2 level and lactate levels, which is detected by the chemoreceptors. As well as this, there is also an increase in heart rate before the exercise, which is the anticipatory rise, which is due to volitional and emotional stimuli. A message is sent to the cardiac control center in the medulla oblongata via the central nervous system. A signal is then sent to the SA node located in the heart via the parasympathetic nerve, where a signal is stimulated. The signal sent also increases the heart rate and means that more blood will reach the working muscles. After a few minutes, the body is working at steady state, which means there is no increase in demand for oxygen, so the heart rate will plateau. After exercise, there will be a rapid decrease because there is a small oxygen debt. Mo Farah's resting heart rate is 33 beats per minute. As a professional athlete, his cardiac hypertrophy, which is where his myocardium has increased in thickness, which means his heartbeats are more forceful, allows his heart rate to be lower and his stroke volume to be higher. Because of this, his cardiac contractions are stronger. Stroke volume during steady state exercise. During steady state exercise, stroke volume will rapidly increase. This is because there is an initial increase in demand for the exercise until it reaches its SV max. Then there is a slight decrease, which is due to the net increase being greater when the SV max is not reached, but the heart beats faster than if the atria fill up to the SV max and the heart beats slower. Stroke volume will plateau because the body is not increasing the demand for oxygen. Then there is a rapid decrease in stroke volume because there is a small oxygen debt after the exercise, and less oxygen needs to be pumped around the body. According to interactivephysiology.com, the average resting stroke volume is 70 milliliters per minute. However, the stroke volume can vary between different people. For example, an elite athlete will have a higher stroke volume. A stroke volume is the amount of blood pumped with every heartbeat. With elite athletes, they have cardiac hypertrophy, which is where the myocardium has increased in thickness. This leads to more forceful contractions and means that more blood is pumped around the body with every beat. According to genreviews.com, an untrained individual's stroke volume at rest is on average 50 to 70 milliliters, beat increasing up to 110 to 130 milliliters during intense physical activity. An elite athlete's resting stroke volume averages 90 to 110 milliliters and will increase to as much as 150 to 220 milliliters. Stroke volume also includes venous return, which refers to the body muscle pump where contractions occur on either side of the veins, which forces blood back to the heart. In trained athletes, the muscle pump will be stronger and the blood is able to get back to the heart faster. While stroke volume may increase rapidly initially, the increased heart rate will not allow the chambers in the heart to reach their SV max during every beat. Cardiac output. Cardiac output is the volume of blood that is pumped around the body every minute. The average cardiac output is around 5 liters per minute. During exercise, this will gradually increase and will then plateau because the heart rate and stroke volume both plateau. Cardiac output will plateau as a result of this. The cardiac output during exercise rises to around 35 liters. There is then a rapid decrease in cardiac output after the exercise. The cardiac output will increase during exercise because the heart rate and stroke volume both increase during exercise and then plateau. The measurement for cardiac output is heart rate times stroke volume. For heart rate in exercise, there will be an increase before exercise due to emotional and volitional control, which is known as the anticipatory rise. This will lead to a gradual increase in cardiac output as well. For blood pressure, there will be a slight increase in systolic pressure and then a plateau, and the diastolic pressure will either remain the same or slightly decrease. Systolic pressure will rapidly decrease to normal because the heart rate is not pumping as much blood after the exercise is finished. As well as this, the heart is not pumping blood with as much force and diastolic pressure increases back to normal. Systolic pressure will increase because more blood is being pumped around the body, and as a result the heart is beating more forcefully. As well as this, the diastolic pressure will decrease because of vasodilation. This is the relaxation of the atrium will mean that the veins that lead back to the heart will open wider and blood pressure is reduced. According to Blood Pressure UK, even after exercise and during exercise there should not be a huge change in either blood pressure.